I'd like to talk about building a linear or quadratic function from a table. Oftentimes in real-life applications, you are just given data. How can you tell if the data is linear or quadratic? Let's consider this example. Use an input-output table and differences to find a linear function for the sequence of data 3, 7, 11, 15, 19. Let's make an input-output table. Let's make the inputs 1, 2, 3, 4, 5 because we have 5 data points, and the output's the value of the sequence. So you should have an input table where the input x here is 1, 2, 3, 4, 5, and the output y is 3, 7, 11, 15, and 19. Okay? So that's what you should do first. Now, let's find the first difference. What the first difference means is you just subtract the difference between the first two values. Take the second value minus the first. 7 minus 3 is 4. Take this one. 11 minus 7 is 4. Take this one. 15 minus 11 is 4. Take this one. 19 minus 15 is 4. You'll notice that the first difference is always the same. So it's easy to find the next items in the sequence if you were asked to do that. Since this goes up by 4, by 4, by 4, by 4, the fifth item was 19, so the sixth item should be 19 plus 4, or 23. Whoops, there we go. And the seventh item should be 23 plus 4, or 27. Okay? So it's not too hard to find these additional items if you know that first difference. If the first difference is constant, you have a linear function. A line would fit this data. And that first difference is actually the slope. You might recall from Math 93 that the equation of a line is given to y equals mx plus b, where m is the slope and b is the 0b is the y-intercept. We can find the equation like we did in Math 93. Since the first difference is the slope, and the first difference is 4, we could write that down. Now, take a point from the table. I could take the first one, 1, 3. So x equals 1 and y equals 3. We know that point has to be on the line. So we could say 3 equals 4 times 1 plus b. Or 3 equals 4 plus b. Or b equals negative 1. So my final equation is y equals 4x minus 1. Now what's useful about this is if I want to find the 100th term of this sequence, I could just plug in 100 in for x, do the math, and that would give me the y. So that's kind of useful. Here's an example I'd like you to try from yourself, or here's another point. Since y-intercept occurs when x is 0, we can also use the table to find the y-intercept. We knew that this was 4, this was 4, this was 4, and this was 4. That means the value before 1, which is the y-intercept because the input is 0, has to be 4 less than 3. Well, what is that? That is negative 1. So again, you could say y equals mx plus b, y equals 4x, plus b here has to be negative 1, and that's another way to do that. Now, I would like you to try a linear example on your own. So you might want to hit pause at this point to try this on your own. Okay, let's see how to do this. I'm going to create an input-output table. Input is x, output is y. 1, 2, 3, 4, 5. I have 5 data points again. And 4, 8, 12, 16, and 20. First difference, notice 4 to 8 is 4, 8 to 12 is 4, 12 to 16 is 4, 16 to 20 is 4. So my slope is 4 because I have a linear equation because the first difference is constant. Now, as far as b goes, I can either plug in a point, or since I know that this went up 4 each time, I know I would have to go back 4 to get 0, and 0 would have to then be 4 minus 4, or 0. so b is 0, so y equals 4x plus 0, or just y equals 4x. Now what about quadratic? Quadratic functions are similar to linear in that you are given a set of data, like this case, 14, 25, 14, 29, 50, 77. And I can create an input-output table for this by making my inputs 1 through 5 again, because there are 5 data points, and my outputs 5, 14, 29, 50, and 77. But this time, if I do the first difference, well, what do I get? I get 9 here. 29 minus 14 is 15. Oh, goodness, these are not constants. 50 minus 29 is 21, and 77 minus 50 is 27. But if I look at, so the first difference is not constant. That means this is not linear. However, I can do the second difference. Let me copy down these first differences here. The first difference is the subtraction between consecutive terms in your sequence. The second difference is the subtraction of these first difference. 15 minus 9 is 6. 21 minus 15 is 6. 27 minus 21 is 6. Notice the second difference is the same. This means the data is quadratic. So in summary, if the first difference is the same, then the sequence of numbers is linear. If the second difference is the same, then the sequence of numbers is quadratic. Okay, so let's see how to fit a quadratic function a little harder from the table. Now, you might remember from section 8.1 that a quadratic function is y equals ax squared plus bx plus c. Now, it turns out that the second difference is equal to 2 times a, where a is this coefficient, and the y-intercept is 0, c. So we can find these values from the table. Here's my table. First of all, that first difference we have to write down again. 9, 15, 21, and 27. And the second difference was 6, 6, and 6. So I know that 2a equals 6, which means a equals 3. So I have my a. I've got to have that. Now I need both my b and my c. To find my c, I can work backwards from the table. So this was 9, this was 15, this was 21, this was 27, this was 6, this was 6, this was 6. Now, you know that the first difference keeps going up by 6. That means the difference between the 0 input and the 1 input, the second difference had to be 6 also, because in a quadratic function, the second difference is constant. Since these are going up by 6 each time, what number plus 6 equals 9? That would be 3. So here we have 3, 9, 15, 21, 27. For my first differences, that would give second differences constant of 6. So what plus 3 is 5? That would be 2. So this value 2 is c. So I have 3x squared plus bx plus 2 so far. How do I find b? I choose a value from the table. Let's choose 1, 5. So x equals 1. And y equals 5. So 5 equals 3 plus b. Excuse me, lights went off again. Woohoo! Okay, there we go. Plus 2. So 5 equals 5 plus b. b equals 0. My final quadratic equation is 3x squared plus 2. Okay, I would like you to try one now. Fit a quadratic equation to this sequence: 3, 9, 19, 33, and 51. You might want to hit pause and try this yourself. If you're ready for a solution, here we go. I'm going to make my input-output table. And I want to remember, find this. So I need A. To get A, I need to find the second difference. So the first difference here is 6, 10, let's see, 14, and let's see, that should be 18. That makes a second difference of 4. The second difference is constant, so this is quadratic. That second difference equals 2 times A, where A is the A in the quadratic equation, so A has to be 2. To find the C, let's copy this table again. I'm going to do 0, 1, 2, 3, 4, 5, 3, 9, 19, 33, and 51. First difference, I'll just rewrite these values here. And second difference, 4, 4, 4. Since this value is 4, this second difference has to be constant. This value, the first difference, had to go up by 4. What number plus 4 is 6? That would be 2. Since the first difference is a difference between the 0 input and the 1 input, it'll go up by 2. That would be 1. This value is C. So far, I have A equals 2 and C equals 1. So I can write down what I have. Now plug in a point from the table. Let's just pick 1, 3 again. Might as well be easy. 3 is Y, 1 is X. That gives you 3 equals 2 plus B plus 1. 3 equals 3 plus B, or B equals 0. So final equation, Y equals 2x squared plus 0x plus 1. That is my quadratic equation. I hope you have found this video useful in solving some of these problems.